This is 2014, number 6, and it's looking at the Taylor series one. Okay, so pretty much the question gives us that f of x is this Riemann sum, and it starts at n equals to 1. So if you wanted to find f of x, you could, right? That's just plugging in all of these terms. F of x is defined as this infinite polynomial, right? So start with n equals to 1. If you plug in 1, it's going to make this just a positive. It's going to make this 2 to the first over 1, which is just 2, and then you get this. So the first term is just 2 times x minus 1. Okay, now plug in n equals to 2. So we're going to get a negative from this. Plug in 2, you get 2 squared over 2, and that's just a 2 times x minus 1 squared. Now plug in n equals to 3. It's going to make that positive. That's going to make 2 cubed is 8 thirds. X minus 1 cubed. Okay, plus dot, 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 dot. And of course, this itself is the general term for the function. Okay, so the first question actually doesn't really involve that. I just kind of wanted to show you what you could do here. So part A says, find the radius of convergence. Now, finding the radius of convergence is essentially the same thing as finding the interval of convergence. And to find the interval of convergence, I can't think of an example that we've done where we don't want to use the ratio test. Reminder that the ratio test is looking at the limit of a to the n plus 1 over a to the n as n goes to infinity. Now, I just want to remind you that this original function, f of x, is an alternating series. So it's negative 1 to the n plus 1. That makes it alternate. If you look at the ratio of like the 100th term to the 99th term, or the 1000th term to the 999th term, it's always going to be a negative. So you can or you cannot, if you want to, you don't have to include this alternating part in the ratio test. It will always give you a negative. And I'll show you why, but you can just skip that if you want. And again, whether it's a negative or a positive, it doesn't matter. You're going to set that limit in between negative 1 and 1 regardless. Just as a reminder, if you do this, or you do this, that's the same thing. If you multiply everything by a negative, everything just switches, the sign switches, and you get this. These are equivalent statements, okay? So if we did this full thing, we added 1 to everything, right? You're just shifting all the indexes by 1. This is just like we used to do, right? That's a to the n plus 1 all over then, negative 1 n plus 1, 2 to the n, x minus 1 to the n, all over n. And if you look at the limit as n goes to infinity, L'Hopital says the n plus 1 versus n is nothing as n goes to infinity. This guy and this guy is going to create a negative 1, which again, I claim down here that doesn't really matter. 2 to the n plus 1 over 2 to the n is just 2, and then x minus 1 to the n plus 1 over x minus 1 to the n is just an x minus 1. So the ratio test tells us that negative 1 is really silly, and so we want to set the result of the ratio test, if we want it to converge, in between negative 1 and 1, divide everything by 2. If you wanted to stop there, you could see that the radius goes from 0 to a half and down to a half. Now this minus 1 just shifts it, so if we added 1 to everything, we'd get the real interval here. But that radius didn't change. It's still down a half and up a half, okay? So our radius of convergence is a half. Everyone okay with all that? And again, we're not actually even finding the interval. We don't have to look at the endpoints here. We don't have to really, worry about that. So we just wanted to find the radius. Okay, part B says, find the first 3 non-zero terms and the general term for the derivative. Okay, not too bad. So just take the derivative. Now first, you could just take the derivative of these guys. If you want to find the first 3 non-zero terms of the derivative, then you could just look at the function that we already wrote up here and just take the derivative and the derivative and the derivative, and you'd get it. And we'll make sure that checks out. But you can also just take the derivative of that. As a reminder, you're taking the derivative with respect to x. So if it just has an n in it, those don't really do anything. They just chill out, right? This is an alternating series, so the derivative is also going to be alternating. This is just 2 to the n over n. We don't have to worry about that. We're taking the derivative of the x, right? So take the derivative, bring down the power, decrease the power by 1. Those ends happen to cancel, and we're left with a function for the derivative. Now, if we want the first 3 non-zero terms, we just got to plug in n equals to 1. So let's plug that in. N equals to 1 is going to make this positive. It's going to make this 2 times x minus 1 to the 0, which is just 2. Sweet. There's the first one. Now plug in n equals to 2. It's going to make this minus. N equals to 2 makes this 2 squared, which is 4. X minus 1. 2 minus 1 is 1. Good. Next term, n equals to 3. 3 is going to make this positive, so plus 8, 2 cubed, x minus 1. 3 minus 1 is 2. See how I did that? Now look what happens if you take this derivative. You get 2. What happens if you take this derivative? You get negative 4 x minus 1. Check it out. Take this derivative, bring the 3 down, it'd be 8 x minus 1 squared. Exactly what I have here. So taking the derivative term by term is the same thing as taking the derivative of the general term and then plugging in. And then of course we get the whole minus dot 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 dot. And then this guy is the general term. Negative 1 to the n plus 1, 2 to the n, x minus 1 to the n minus 1. Okay with that? So part B said find the first 3 non-zero terms, 1, 2, 3, and the general term, bingo. Okay, part C says the Taylor series f prime is a geometric series. And you look at it and you're like, oh, look at this, f prime, it is a geometric series. Okay, it says find the function f prime to which this series converges, meaning use the fact that we know geometric series have sums equal to a over 1 minus r, and then use that to actually find the function. Okay, here's what they mean. So look at this. This is f prime. That's f prime, and they tell you it's geometric. Remember, geometric series are always ar squared plus dot 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 dot, and you can see a is equal to 2, and r is negative 2 times x minus 1, right? What do you multiply by each time? Where you multiply by a 2, actually a negative 2, and then you get an extra factor of x minus 1 every time. So our a value is 2, and our r value is negative 2 x minus 1, which means our sum, which is our f prime, is 2 over 1 minus negative 2 x minus 1. Okay, so that's going to be that negative and negative are going to cancel each other out. And it's going to give us a 2x minus 2. So we get 2 over, and again, do that as slow as you need to. That's a 2x, and that's going to be 2x minus 1. Okay, that's our function. Excuse me, that is our derivative, right? That's f prime. And then we're going to use this fact, the fact that we know this is equal to f prime, to find the function, because we can just integrate. So if you integrate this, right, the integral of f prime, the integral of 2 over 2x minus 1 dx is just the natural log of 2x minus 1 plus some c. Okay, but if you look up here at the function, we know that f of 1 is 0, right? If we plug in 1 to all of this stuff, all of those terms drop away and we get 0. So what happens then, if we know this is our function, we just figured out that c was equal to 0. So bingo, there is our function, right? We have the function because we knew the derivative. We knew the derivative for the, of this particular one because we knew that the derivative was a geometric series, and we know how to sum up all geometric series is a over 1 minus r. Lots of times they call it a sum, but in this case we actually found a function because they're x values. Okay, so this is 2014. It relied on ratio test to find an interval, to find a radius of convergence. We didn't have to write out this function if we didn't want to. We took a derivative of a function, knowing that we're really just taking the derivative with respect to x. We wrote out the first 3 terms of the derivative. We realized that this is a geometric series in which its sum is an a over 1 minus r, which gave us the derivative. And then with the derivative, we can integrate to actually find the function, which means this is what this is. And you may not have recognized it, but think of the natural log that we kind of memorized. This is essentially kind of the natural log shifted over by 1.